Hello and welcome to Data
To po
Science.
angielsku. Dobra, okej. Trochę się zdziwiłem.
Hello and welcome to Data Science in Industry vlog. Today I'm with Kamil Sijko.
Hello.
Kamil Sijko is the head of the Data Science department in Transition Technology Science. I'm the head of the R&D department, and we closely cooperate with Kamil on many projects mainly in healthcare, but also in some industrial projects. Our teams are mixing, so we have a lot of interesting discussions. Kamil is a statistician. I'm the IT guy. My background is process automation. So, like I said, in every project we are discussing different approach from different fields of science, and today we would like to share these discussions with you. So, Kamil.
Let's do this.
Yeah. First of all, in your projects in the healthcare sector, we are using a lot of statistics.
Yes.
Everyone is asking for the p-value.
Mm-hmm.
From my perspective, from the industry point of view, nobody really cares about the statistics, the p-values. I mean, the system must work. The accuracy of the predictive model must be high.
Yeah.
There must be some results of the optimization that generate cost savings.
Mm-hmm.
The p-value, really, I think only in two or three projects we had to do some statistical tests and calculate p-values, and it was not because of the customer requirements. It was because we wanted to be sure that our recommendations, the things that we find in the data, are correct. What is your perspective on this? Do we really need the statistics?
Absolutely. So they have some unique qualities, but actually this is a funny story because the origin of some of the statistical tests, at least, maybe the good example is one of the most popular tests in medicine, the t-test. It was actually invented in the industry. So, this is, I understand that now people have this distinction, machine learning, data science versus statistics, although you can discuss maybe whether statistics, how those terms overlap, but still there is this distinction. But the origin story is that there was a guy named William Seeley Gossett, who was chief brewer, I guess, in the Guinness brewery. And he was looking for a way to tell whether his brews are actually in good condition. So he wanted to take a sample from the brew and tell whether the whole thing, it was, I suppose, enormous. And it's not possible to measure every bit of it, right? But what you can do is you can extract a sample, and based on the sample, tell whether it is as it should be, as the parameters are in line with the guidelines or not, maybe. And this was the origin story of the t-test, and this is one of the tests that is actually used widely in the clinical trials right now.
Oh yeah, that's true.
So this is they are connected. So the industry
From alcohol to the healthcare.
Yes, exactly. So and that is actually a great example of one of the key reasons why the statistics are needed, because they enable you. Because in medicine you are rarely, of course, if you're a physician, if you're a doctor, you are interested in your patient. That's always the case. But if you're conducting a clinical research, then actually you are not interested in this particular patient. You are interested in the population. Take COVID vaccines, for example. If let's imagine you are the participant of the clinical trial, and it worked for you. You were not infected, so that's good for you. But actually we are not interested in you. We are interested in all of other people who will come after you, whether they will be successful, what is the estimate, how many of them will be not infected after vaccination. So this is the question. And statistics answer this particular question really, really good. So they are good in abstracting data points to whole populations, and this is what we want to know. We are not interested in the data points. We are interested in the populations, the more abstract thing. And this is, for me, this is magical. So we can know things about the whole Poland, the whole world, based on just a small sample. So in a clinical trial, you can have just a hand of subjects, let's say, I don't know, 15, 20, sometimes hundreds, but it's nowhere near the population, and you can still tell something. And the other magical characteristic, of course, it's not magical, it's scientific. It's based on math, so you can actually show a proof how this sample you got, given that you fulfilled all the assumptions, can generalize to the population, and also you can give exact numbers. How precise are you? So you can tell that the number for the population is, for example, if you're measuring this COVID vaccine, that the 80% of the people will be without infection, and you can give exact 95% confidence intervals that show you where is this true value that you haven't observed, but you have a really good estimate of where is it. So that's I guess the whole point here.
Yeah.
And
in industry, those confidence interval are used. So there is a point where we are using the statistics. If you have to forecast the heat consumption, energy demand, gas demand, such things, it's always good to show the confidence intervals. And I think also that in the healthcare sector, doctors, they need to have proofs on the limited samples, because then if they will change the treatment path of the patients based on the clinical trial, the scale up is enormous. So the whole everyone on the planet can then take this drug. So they need to have a very strict proof on the limited sample. But on the other hand, in the industry, people are rather focused on whether it's working or not, whether it's generating savings or not, and this is the proof. So the proof is that there is no some scale effect that, but such big scale effect as in the healthcare sector, but it's better to make those all those predictive models, implement them, and you see the final effect, the final proof. You don't have to wait, for the whole people in the world to take this drug. It's working or not. It's generating savings or not. And also the other thing is that the variance in the historical data is usually it's not so big. If we are, for instance, if you are implementing the optimizer that generates savings, usually it means that it will force the process to work in different operating points than the history. So we don't have samples to compare. In fact, usually.
So that's actually the other general point of difference between those techniques, because the machine learning and data science is focused more on prediction. So you have new data and you would like to predict what will be the outcome. And statistics is about generalizing the old data to the population. So the purpose of the operation is different, right? So that's it. And also I think the one of the things you also mentioned is also related to the purpose, because and to the cost of the error, I guess, maybe.
Yeah, that's
because
also true.
if you're generating savings for the factory, then if you're wrong, then you will generate a little bit less savings, maybe. But if you will order the wrong drug for the population, then you can actually kill people. This will imply severe implications for you. And also, if you think about it, then the good example is what we have in cars. So the industry is trying for a long time to introduce the autonomous systems, and we have a lot of the systems already on board. But still, we don't have fully autonomous cars. I guess the huge reason for that is accountability. Who will be responsible in case of an error?
Yeah, this is a hot topic.
And if you're a doctor, if you're using statistics, then you have this nice feature that there is a mathematical proof, and you did nothing wrong here. So you're clean. You have data. You have clean reasoning from the data to the inferences. And if you've taken care that your sample is all right, that all the assumptions are all right, then you're bulletproof basically. And in medicine, this is important.
True, but on the other hand, it's not that machine learning is not used in the healthcare sector. We have a lot of common projects where we are using machine learning techniques in the healthcare sector. So maybe you can share one of such a project.
Yeah, and so exactly as we said, it's all about the purpose, right? So it's not like we are doing those in generalizations from the sample to the population all the time. Sometimes in medicine, we want to know what will be the new outcome. So sometimes doctors are interested to have a system that will classify patients, what will be the outcome if I do this treatment, what will be the outcome if I do this treatment, what is the chance for relapse or something like that. Or simply they would like to browse the huge, vast amounts of data to see what other maybe potential relationships are in there in the data. So this is, I guess, the most important reason why we're using machine learning in medicine. So we are frequently applying it to, for example, for genomic data, just to scan the data and to see what does the machine learning see in the data. What is potentially there that we might have missed. We don't yet have a hypothesis that, for example, this particular gene or RNA or something else has any relation with the outcome we are interested in. So, for example, we've been doing in the EPISTOP clinical trial, we've been doing this kind of analysis. This was a study where only 100 of patients have left after them more than 33 terabytes of data. So a lot of data about the patients, and we are interested in why some of them are developing drug-resistant epilepsy and some not. So, to handle this question and to somehow, use this 33 terabytes of data to give some kind of an answer to that, we applied machine learning and we scanned the data to see what, some techniques which are explainable to see what signals may be potentially interesting. And of course, in this particular example, we haven't deployed that to production. So we are not using this classifier to predict whether actually somebody...
some kind of fishing expedition. So it generates new hypotheses for
exactly.
clinical trials.
So the doctors are given a list of signals which might be potentially interesting, and what they can do with that is to plan proper clinical research to investigate further. So we are, giving some kind of preliminary evidence that this might be interesting.
Yeah, I agree. It was a very interesting project. And if we talk, about the machine learning, then another question should be about the data, right?
Yeah.
So in the industry, we have processes, we have devices, they have their own measurements, sensors. So usually the crucial parameters are measured. Sometimes we think crucial parameters are not measured, then we can estimate it this way or another. Of course, there are problems with missing data from time to time. Sensors have their own accuracy, so there's always some kind of a noise associated with a measurement. But generally speaking, the quality of this data is okay. In every project, we are finding some missing values, some incorrect values. Sometimes, the sensors are mixed, are not placed in the proper part of the technological processes. So this is normal. And how about the data from the healthcare sector?
Yeah, so that was actually when I came to TT, where a lot of the data comes from the industry. That was my first impression. Wow, how good the data is! It's wonderful. This, it's so clean, so few missing points, and so on. That was great. And what you can do on this data. So if you're making predictions, how powerful they are. So how this whole data science and machine learning, how great it works here. That was a great experience. But in case of medicine, in case of fields where the data comes from human beings, well, basically the problem is that there is a lot of noise on the measurement. So my initial experiences with the data science were actually in the field of psychology, where this is probably one of the messiest fields, where there are questionnaires. So the way and there is no sensor that can measure your intelligence. There is only a test. You can ask a couple of questions, and based on that, get some kind of idea how intelligent a person is. Or if you would like to judge their character, their personality, there are also tests for personality, but they are basically questions, just simple questions. Based off a handful of questions, you can infer what is the type. And this is messy, so the reliability of those tools is very low. or maybe not all, but usually it's compared, especially compared, what we see in the industry, it's low, and this is one of the problems. So first, you have a lot of measurement error. Second thing is that there is sometimes a human in the middle. So it's not always so clean as in intelligence tests, where you have this key. So if the answer is this, then you assign a point. If not, then no. Sometimes it's like, a clinician has to judge what is the, for example, main diagnosis for a patient.
It generates variance. There are different schools of medicine, different
exactly.
books,
and
different ways of interpretation of the same phenomena.
Exactly, and sometimes we learned that if you try to handle medical data, then it's frequently impossible to do if you don't have somebody who was on site and is aware of the practices there. Because you see seemingly same patients, but one was coded in one hospital, the other was coded in the other hospital, and in practice they might be different because the coding practices are different. So actually we have nice experiences and nice relations with the people who are who run an association in Poland of medical coders. So there is an association of people who handle just the coding, and they try to standardize those practices and try to talk to each other to make those things comparable. But there are lots of issues, so it's a very difficult field, and you have to take this into account. And this is one of the primary problems when you trying to model the medical data.
Yeah, and I think one more thing is the variance generated by the human body, right? So it's much more complicated system than the industrial process, and also we cannot install infinite number of sensors. It's not matrix, right. So it's harder to measure those phenomena in a human body, and the variance generated by patients is way higher than I think in industry.
Yep.
And also I think it's harder for to find this ground truth. Because of this interpretation of doctors. If we cannot measure this ground truth, if make the biopsy, right, or some computer tomography or other things, it's hard sometimes to judge what is the real state, let's say real state of the patient. In industrial processes, this much easier. And I think one also you mentioned this Epistop project, and that we had 100 patients and I think 30 terabytes of data, right? So we have a lot of features and not that big number of samples, and so in many cases we have to apply feature reduction, space reduction, dimension reduction algorithms like PCA or others.
That is correct.
Because it's hard to apply some sophisticated machine learning algorithms if you have not a big number of samples, right?
That's all true. So the first problem you mentioned, this is fully agree that the vastness of the data is especially if we are getting out of the clinical data and going into the genomic data, the proteomic data, the number of the variables you get from this this kind of research is enormous. And the thing is that this makes the machine learning very difficult, because one thing we do in this kind of situation is we usually start with setting up a baseline. So we are just shuffling the target variable, and we are just checking what kind of performance metric we can get if we break the relationship between the target and the data. So this is our baseline. And this baseline, if there is absolutely no relation between the target, so for example, those seizures and the data, this is sometimes as high as 80% of accuracy, 70% of accuracy. So just based on because of the fact that you have only 60 patients and hundreds of thousands of variables to pick from, you can basically build a classifier for everything, and this will be just pure garbage. So you have to be really careful not to and not to give to your customers, to the patients, things that are not true, basically, right? So just
and
just there by accident.
that is why we are applying those permutation analysis, right?
Exactly. Yeah.
On classifiers, machine
Yeah,
learning
yeah.
classifiers. So we are shuffling the labels,
Yeah.
and we check if we can obtain similar results with different association of labels, right?
Yes.
So, and there is once again the statistics that help us to say if it's obtained by chance, or
Yeah.
there is something really that there
Exactly,
is some
exactly.
relation.
So that's other nice feature. But still, and you know, the awareness of this process, of this problem, this is very important, that we are aware of it, and we are very careful in explaining to our clients, to doctors, to patients, what they can expect from the machine learning based on this particular data set. So in case of Epistop, what we told them very strongly and what we emphasized was that this is not ready for production. So this is not something you can take and apply to your treatment. This is something you can take and apply to your research. So that's what it's good for.
And that is why we had new projects on this topic with
Yes.
new hypotheses. So this is a continuous process, right?
Yeah, because I think this is hard to emphasize enough, because you know, now in times of Kaggle, where this medical data is freely available, there are people who are just using machine learning and are maybe a bit too optimistic with regard to what you can do with that, or what can machine learning in this particular situation, what you can expect of this outcome. So this is important to be realistic here.
Yeah. And this is interesting that we are using, sometimes you are using exactly the same methods in industry and in the healthcare sector. If we are, predicting the risk of the failure of a pipe in the district heating network, well, this task, I mean, from the algorithmic point of view, is very similar, usually exactly the same as predicting the risk of a disease, right?
Yes, progression.
Or the progression or other stuff. However, the data and the variance of the data, the quality of the data, the number of data, this is something that differentiates
something else. Yes.
Those sectors.
Yeah, and again, we could find statistical techniques which were specifically designed for the industry. Like, for example, in case of the survival analysis, there are those models which are specifically designed for accelerated failure time. So if you're putting a lot of stress on some part, just to see how much it can endure, so there are specific statistical models just for this situation, which is usually in the industry, because this is something you wouldn't like to do for a human being, right? You wouldn't like to stress anybody to see when it fails.
Exactly.
But you can do that to the mechanical parts, for example.
Yeah. Okay, so on the end, I wanted to ask you about the picture that you made, but first I need to open it. So
sure. Okay.
So Kamil, I very like this picture.
Okay.
You made it on the conference, right?
Right.
So the conference about and your speech was about the key factors that are crucial for a successful data science project, right?
Yes, based on our experiences, exactly.
Okay, and sorry it's in Polish, but I especially like this part that we are looking for hackers to our team. So our team is built on hackers. You call them hackers, I call them data Rambo. So we are data Rambos or hackers, depending as you will. But how do you understand that someone is a hacker? We would like to, crack to IT systems of our customers, or what?
Yeah, that's the tricky part, because many people now, in the pop culture, hacker is exactly what you said. Basically, a criminal who is trying to, break into your system, steal your data, steal your money. But in reality, and if you look for the true meaning, the original meaning of the word, of the phrase, a hacker is actually very different from that. So what this cyber criminal is, who this is a cracker. Sometimes he is referred to as a cracker, and a hacker is just a guy who is, basically interested in solving problems. And the important characteristic is that he is using sometimes tools which were not specifically designed to solve that problem, to actually solve it. And a good example is if you've been watching the TV series MacGyver. So he's the guy who is usually using a duct tape and some random tools which are lying around to build a helicopter or some other automated machinery. This is exactly what's on the picture. So first of all, I was trying to explain that we're not talking about the cyber criminals, but we are talking about people who are very resourceful and who are capable to use whatever is possible to solve the problem, and they're very highly motivated to solve the problems. And there are actually multiple characteristics of a hackers. I used the concept of a hacker attitude. It's not mine. It's something you can find online. And there are actually a couple of important characteristics that you can look in people to distinguish those who are actually hackers from those who are not. And this is something also which is important and nice, that you can work on those qualities. It's not like people are born hackers. If you're not yet a hacker, you can try to be one if you're working on this attitude. So a lot of it is about the attitude.
Yeah. So if you was not trying to escape from the hospital when you was 3 years old, 3 days old, you still can be a hacker, right? In your professional life. Yeah, but I fully agree with this. To solve a problem, this should be the main goal, and there are many ways to solve the problem. And it is good if you have a team of hackers, because that it means that you have a lot of interesting discussion how to solve it with the tools that we have, with data that we have, with assumptions that we have. So problem solving, this is very important, and I think this is also something related with generally Polish data scientists, because in early 80s, in late in 90s, we didn't have easy access to all those IT stuff, to IT systems, and there was a lot of problem solving to install even a game, or the system.
That's true. Lack of resources is one of the factors that pushes you into being a hacker, because if you don't have resources, you have to cope with what you have. So that's one of the reasons.
Exactly. And so maybe the last question on this picture, error Python.
Yeah, so that was actually the first point of entry to this whole speech, because many people are asking this question, error Python, and actually I had another conference entry on just this question. And the answer to that is that whatever works for the project, basically, or whatever you know already. So if you're a hacker, if you have this attitude, then basically I don't care how what will be the language where you will solve it. There are some interesting, qualities to those languages that, one is a little bit better in this, and the second is a little bit better in this other thing. So, you cannot hide that, for example, R has bioconductor, which is great for analyzing biological data. So if you would like to
better statistical models, right?
Yeah, a lot of that. So a lot of statisticians are actually developing their work in R, and sometimes it is ported to Python if it's popular, and sometimes not. So your tool set, if you're using statistics, if you're working with medical data, you have a lot more tools to choose from. It's not like Python is not capable of developing the same outcome. It is, because they're both programming languages, so you can do anything in both. But it's if you have the tools at hand, it's so much easier. And on the other hand, if you're using Python, if you're using this for machine learning, PyTorch or things like that, then sure, there are some modules and libraries that enable you to use Keras, for example, in R. But if I were to use Keras, I would probably go for Python, because it's native, and usually you will find more support for the things that might go wrong, or resources, and it's tested better, and so on and so on. So yeah, so the first and foremost, you have to have a great team, and then the tools go second.
In many projects, we are mixing those two languages, right? In healthcare sector as well as industry. In one of the last videos, I was talking about optimization of a district heating network. So I think that deep neural network that was forecasting the heat consumption was made in Python. The dynamic machine learning models of the network was made in R,
Mhm.
and the optimization algorithm was made in C++ and then transported to Julia.
Yeah.
So three languages. And the same in our projects, right?
Yeah.
Some of the classifiers are made in Python, especially this machine learning part. The statistical part is made in R, and
Yeah,
there is a lot
but
of mixing.
It's not the case in all of the companies that they mix technologies like this. I was once working for a company where they, just claimed that we are investing in Python and Java. Those are our tools. We are investing in this stack, and we are, whatever we do it with Python or Java. And that was working for them, I guess, okay. But I very like this attitude that we have here, that, we are flexible, and it's not about the tools, it's about the problems and about the people. I think this adds to the diversity. If you have this atmosphere of solving problems, you need to have multiple ideas, very diverse team, diverse takes on the, how to solve this problem. And if you have this soup, then you can extract some nice ideas from it. So if you have multiple languages at hand, you can do the same. You can extract nice ideas and nice solutions to your problems then. So I like it very much.
Okay. All right, Kamil, thank you very much for interesting
Thank you.
discussion. Tartul.
Sure.
Okay, and
Okay.
bye-bye.
Bye.